Swayam Prabha. Digital India. Educated India.
Hello, today we are going to discuss another important gauge called spinning rotor gauge and ionization gauge and its improved version called Bayard Alpert gauge. These gauges are more sophisticated compared to the gauges that recently we discussed on thermal conductivity type Pirani thermocouple gauges. These are secondary gauges, but out of that spinning rotor gauge is a primary gauge for high vacuum applications, where there are some natural limitations of McLeod gauge below -5 torr because of vapor pressure of the mercury, etc., even with cold trap. But that overlapping range, that gauge can be used to calibrate this spinning rotor gauge, and with some linearization people have done a lot of work in the initial days. Even though a lot of work is going on, in fact, I would say there is a lot of scientific research scope in developing a reliable primary vacuum gauges, which can give high-tech processes, particularly in space technology or nuclear or electronic industries, semiconductors, so that what you are measuring is meaningful and reliable, and it can be related to the quality of the process. But now at present people are just switching on the gauge, they do not even bother about that. Got -7 torr, -8 torr, switch on something, -5 torr, metallurgical furnace on, -6 torr, -7 torr, okay, electronics things start things, -9, okay, immediately nuclear particle accelerators they start. Whether it is 5 into -9 or 4 into -9, yesterday it was that, cross correlations, it is a big field. But unfortunately, people feel that pressure measurement is a side thing. No, that is related to the process, and a 3 into -7 torr is different from 8 into -7 torr. But somebody may say, it is of the order of 10 power -7 torr compared to 1000 millibar. It is not like that. So, we need some sort of standards at high vacuum level. Using that, some friendly gauges also are required based on some secondary principle, mostly ionization principle, because thermal things will not work. They are mostly bulk property of gases and little bit of molecular transitions, like residual gas conduction, all heat transfer related. But when you go for high vacuum, none of these things will work because of error analysis, etc., from radiation, and we have seen that solid conduction and all. We have to depend on some other thing. We told when we are discussing thermocouple gauge, heat transfer gauges, thermal conductivity principle. So, now is the time to go towards higher vacuum side. High vacuum side means going is production, that we have already discussed all pumps. Then measurement. And this measurement is a molecular level measurement. It is no more gas, it is not a pressure of a gas, it is the pressure of the molecules. Definitions itself is vague. Okay, which pressure we are talking? It is a force per unit area. Where? So, it is, we are thinking from P is equal to NKT. Okay. There is P is equal to 1/3 MNC square bar. P is also F by A. Okay. So, there are ways to do this, and some people say that thermal energy is responsible for this motion and they are kinetic theory of gases. So, these are all interrelated pressures, thermodynamically higher pressures, but in molecular level statistical Maxwell-Boltzmann statistics. So, gauges have to understand these implications, the high vacuum gauges, they are not measuring a gas pressure. And if there is a sort of primary gauge that should also be related to some fundamentals, if not like a YouTube manometer or McLeod gauge, which are good enough for fundamental gauges for the thermal conductivity gauges, and secondary standards like capacitance gauges are we have seen. But here we are going to talk of some standards for high vacuum gauges. Then we will see one by one ionization gauge using hot cathode, ionization gauge use penning gauges, then inverted packed electron gauge. These are all standard words. Those who are in the industry in semiconductor, metallurgy and space and nuclear, they know very well these 4-5 gauges. But those who are in chemical, pharmaceutical and force applications or lifting applications, they are not that much bothered about these gauges, spinning rotor or ionization, because their vacuum level is at the best 10⁻². Recently with molecular distillation coming up for making a very high quality drugs, etc., and ultra high freeze drying of subliming water at -4 torr using liquid nitrogen traps and all, things are changing towards high tech, but they are very specialized applications. Otherwise, most of the chemical and pharma and other process, mechanical process are Pirani gauge, thermocouple gauge, capacitance gauge, and they will use YouTube or McLeod for calibration. But what about the semiconductors? And in between metallurgy is there, and special coatings, engineering coatings, then nuclear processes and space technology, space simulation and electronics, chip manufacturing. So, for that some gauges have to be there, because without cleanliness you cannot make any meaningful thing in a particle accelerator. 10⁻⁹ torr, few particles are moving and they are ionized and they are made to rotate at high speed with huge amount of electron volt energy, few very high level of energy. They will hit each other without getting scattered, without losing energy. These are called particle accelerators, linear particle accelerators, circular particle accelerators, all of them. For example, LSC, costliest experiment ever done, even now it is going on, few kilometers ring of vacuum and ultra high vacuum. So, all these things, when people are working on it, they must keep in mind the level of vacuum should be measured, whether it is -9 or -8. It makes a lot of sense. 10 times more density will be there, collision cross sections of atoms or ions will be 10 times more. The results that you are getting from LSC will be meaningless if you are maintaining -8 and instead of -9. But your gauge is showing some wrong value and you switch on, you will not get results. Similarly, space simulation, 36,000 kilometers, etc., satellite is sitting at 10⁻⁹, we are simulating at -7, behavior will be different. So, it is equally important to have some standards, some meaningful experiment gauges whose output will be electronic, and so that you will get digital display for comfort and which can be computerized, all that. We are in that game now, we will go ahead into that direction now. For that, let us start with a sort of primary standard, but it is based on not a gas dynamics, based on molecular drag dynamics. Afterwards, we will go for secondary gauges which use this spinning rotor gauge for their respective calibrations. So, that is why I have clubbed spinning rotor gauge with ionization gauge and Bayard Alpert gauge. And in the second class, next class, we will also give cold cathode gauge, penning gauge and inverted magnetron gauge. They are all related to high vacuum ionization principle, which need to be calibrated by a spinning rotor. Which standard you have to use, which secondary standard, what is the reliability, that has to be properly handled by the designer. How much accuracy is required. We will see. So, the concepts that are going to be covered in this lecture are spinning rotor gauge, ionization gauge and Bayard Alpert gauge. I could have easily included penning gauge, inverted magnetron gauge, but lack of time, I have separated them into cold cathode gauge, which I am going to discuss. Towards the end, we will club all of them and talk about some reliability, etc., and we will see how to calibrate in general overall calibrations of various gauges using some fundamental methods like static expansion method, etc., dynamic methods. With that, this pressure measurement is over. Many people think that pressure measurement is a gauge measurement, but if you know after these 5 classes, you will get a different feeling for pressure measurement and how much it is going to be relevant to the control of a process or to the quality of the output coming out of a process. So, this class we will confine ourselves to spinning rotor gauge, ionization gauge, Bayard Alpert gauge, all are high vacuum gauges below -4 torr. They cannot be switched on unless you get -3 torr confirmed by a Pirani gauge. Then only you can switch on, otherwise they will be spoilt. They are costly gauges. So, first we will see spinning rotor gauge. You can concentrate on the figure. It is a small high quality pipe, stainless steel pipe, inside which you try to keep a very high quality stainless steel ball floating. How do you make this little magnetized stainless steel ball? It is not non-magnetic steel, and that ball will be floating because of magnetic fields created by some electromagnets as well as permanent magnets. They will apply forces in such a way under dynamic conditions. When you are driving with some driving coil, then when it is spinning under those conditions, it is stable and it gets floated. Dynamic balance. It is somewhat like magnetically levitated trains. So people are trying to do how to put various forces on lateral and linear and various forces. Okay. That is at atmospheric pressure or little rarefied pressure like hyperloop, etc. But here we are talking about -7, -8 torr, where drag is not a gas drag or anything, it is a molecular drag. Okay. These can be used from 0.1 torr down to 10⁻⁷ torr. Basically, it is a molecular drag on this principle, on this spinning stainless steel ball and levitated with the help of permanent magnets and electromagnets and made to spin with a drive coils, which electromagnetically will drive this using standard induction principles, etc. And suddenly you switch off these drive coils, keep the floating coils, then what will happen? This, if perfectly as per Newton's first law, anything that is happening in space, if there is no reaction force or anything, nobody is there to stop, it will continue to be in its state. But there is something, even at 10⁻⁷ torr, there are millions, billions of molecules. 2.5 into 10⁻⁹ is 1000 millibar. 10⁻⁹ is only 12 orders less. So, it still 2.5 into 10⁶ or 7 molecules are there for every cc. So, in namesake we are talking vacuum. These molecules are quite rarefied in the sense the mean free path is quite longer compared to the dimensions, physical dimensions of the enclosure. The pipes, etc., are all 2 centimeter, 5 centimeters. Mean free paths are already reaching more than 1 kilometer. So, each molecule is independent, but those molecules will hit any physical surface including this ball. So, the molecular density is very important, 10⁻⁷ one density, -8 one density. These molecules, when they hit, which is spinning, and they will try to decelerate, but the drive coils will try to accelerate. Now, a constant spinning motion will come, which is around 400 or 500 hertz type of thing. It will go to that level and it is switched off suddenly. Then what will happen? It gets slowed down because only the retarding force by the molecular collisions are there, not the gas drag, molecular drag. Then it will decelerate. And if you measure the deceleration, electromagnetic principles, after all it is a magnetic ball, if it is decelerating, that you can pick up those things, that decelerating things, because any magnetic field rate of change of thing can be picked up as a pickup voltage. So, here also it is decelerating in the time domain. So, you give some time constants and try to pick it up, and you try to do some manipulations in such a way, finally the signal can be made to be proportional to the molecular density, and that which is applying the drag, and that molecular density is proportional to pressure. A lot of calibrations are required. It is not as simple as what I have told. Lack of time, I am telling little faster, but you can look into this in the net, you will get a lot of ideas very clear. Okay. So, you can read it also if you want. It is a levitated steel sphere, and it can measure as a calibration standard up to -7, and it is a 4.5 millimeter magnetic steel ball, and it is located in a horizontal pipe. There will be pickup coils and there will be drive coils, and magnetic fields are there to levitate. Pickup coils are there to, drive coils are there to rotate it, and stop and deceleration measuring coils using electromagnetic principles. So, while operating what we are driving, we will first drive the drive coil. That magnetic field will be making the ball rotate around 415 hertz. Then suddenly the drive field is switched off, drive coils and pickup coils. Then permanent magnets and electromagnets. And you can superpose these fields. There are ways of doing, there are varieties of these gauges. It is not easy to make, very few companies manufacture, and you have to maintain them as primary standards type at -7 torr under good vacuum. All that precautions you have to take, and throughout 24 hours you have to maintain those standards of vacuum inside, otherwise they will get oxidized and things will start behaving in a different manner. Okay. So, this once this drive field is switched off, then it only gets decelerated now. When it gets decelerated, the decelerating effect by the molecular collisions on the ball, we are going to pick it up. I have already told you, but you can go through these things and understand. There is a very good digital electronics available nowadays with control units. Once signal comes, they know how to do the monitoring or signal manipulations. And these are basically ultra high vacuum gauges. Time intervals you have to maintain, averaging techniques you have to follow statistically, because this is a molecular phenomena, drag. It behaves according to Boltzmann statistics, Maxwell-Boltzmann. It has nothing to do with any other laws at high pressures, okay, like Pascal's, and it is not that drag. It is not the drag that we are going to use in our aerospace and other things. This is not a, it is not a gas drag, it is a molecular drag. Okay. Some statistical things are there in the derivations built in. All that if you see, you can certainly use it as a ultra high vacuum gauge. So, with this much introduction to a sort of primary gauge for ultra high vacuum, let us see the secondary gauges which are more friendly with us. You cannot use thermal principles, you have to use ionization principle, which I told you while discussing thermal conductivity gauges. So, this ionization gauge let us see now step by step. Look at the figure. Those who know little bit of electronics, electronics started from tube electronics, all of you know, diodes, triodes, etc. 78 years back. So, after that time there was no solid state electronics. Afterwards, triode is replaced by transistor, diode is replaced by solid state diode, PN junctions, etc. came. And later several PN junctions making a bistable multivibrators, 0, 1 state, then digital electronics came, then memory elements and switching elements, all of them together with power circuits, power electronics, all together will be the motherboard and varieties of display units based on optical properties, optoelectronic properties. Together we have mobiles and TVs and also our computers. This we will see later. But what I want you to understand is electronics started from vacuum, diode, triode. If there was no vacuum technology developed of simple diodes and triodes, today we will not have electronics field, today we will not have computer science field. We may have only mechanical aspects and thermal aspects of vacuum technology maybe. So, diodes, triodes could be made under vacuum. That is why if you look at the history of electronics, electronics means dynamics of electron. Okay. This electronics starting point was using tube type of electronics, and this will look like a triode having one filament which emits electrons due to thermionic emission. Then there is a grid, that grid will be a perforated grid, and there will be a collector which is a cup type of structure, and if you make a cross section here, it will look like that. There is a circular collector, there is a perforated grid which is circular again, and center point there is a filament, that is the filament, here filament, this is the grid, this is the grid, this is the collector, this is the collector. All this is housed in a glass bulb or metal bulb. If you use metal, you have to use metal to ceramic joints here, they are not short circuited otherwise electrically. And this is connected to the system. And the filament is heated, DC bias will be 0 volt, but AC current or anything you can pass it and you can get a heating effect of a filament, and hot filament will produce thermionic emission of electrons. This is already under -3 torr created by rotary or other pumps, then -5, -6 torr or -7 torr created by turbomolecular pump or cryo pump or diffusion pumps or ion pumps. Under those conditions, the system is exposed. This gas is connected to the system now. So, this is already at -5. These electrons which are emitted from thermionic emission, they go out radially outward, because this perforated anode is connected at a voltage of 180 volts plus. So, electrons will know how to go towards that, nobody needs to tell, they will automatically go. But since it is perforated, the electron while going here, it may miss, and again after missing it will think, oh, its destination is not the collector. Collector is maintained at negative potential. Electron can go to cannot go to negative. So, in between plus 180 to minus 30, there is a potential 0 somewhere. It can go up to that maximum. Afterwards, it will revert back. So, it may oscillate across the grid. In the process, it will have lot of path. In the process, it will meet lots of atoms which are there in equilibrium with 10 power minus 8 tier of the system. So, those atoms will be ionized by these accelerated electrons. That means, you are producing electrons from hot cathode using thermionic emission. These electrons are made to confuse or oscillate across the grid. Acceleration is because of high voltage, and the confusion is because of oscillation is because of perforation, and in the process their path length is increased, they will ionize. That is why it is called ionization gas. But the number of ions will be proportional to number of atoms per unit volume. So, number of atoms per unit volume is nothing but proportional to pressure. P is NKT, that N is the number density, molecules per unit volume. K is constant, T is constant. So, if we can measure N, we cannot measure N directly. N, out of that, a fraction of it will be ionized by these electrons. If you know that as a constant fraction, so we will switch on this current, and we know the ions produced. From the ions, we know the molecular density. From the molecular density, we can relate it to pressure. So, this is how the leakage current measured in the collector circuit can be collected, and that will be measuring the pressure. There will be one circuit for the filament, there will be one biasing for the grid, etc. So, all of them are shown here, you can slowly go through it. So, it is basically hot cathode ionization gas. This gas works up to 10 power minus 8 torr nicely. So, very nice. You are getting very good display, because ionization current, once you have current, you can make a display. Current can be converted into voltage, all sorts of things you can do. And this may be millivolts, milliamperes, but still today nanovolt meters are made. Okay. So, it is possible to use electronics. Electronics took birth from vacuum, now it is used to measure vacuum. So, always you create something which will be helpful to again help you, like cryogenics. It requires vacuum, and vacuum helps cryogenics. Without vacuum, cryogenics cannot be there, and best vacuum pump is again cryo pump. So, it happens in measurement also. Because of vacuum, semiconductor electronics came. Because of that, electronic digital circuits, everything came, and this digital electronics can be again helping the measuring things, measuring ionization currents very accurately. So, it is a give and take thing. It is a hot cathode ionization gas. Okay, fine, story is good, sir, I am getting good display, and once in a while I can easily calibrate it with spinning rotor gas. Good, I can make semiconductor, space technology, nuclear immediately. No, suddenly problem came. You get success problems alternatively, you keep fighting. When things get tough, keep going. So, what happens was, that time, after some time, 10 power minus 8 torr, some error is coming heavily. What is that error? Now, little bit observe. These electrons, when they are finally hitting this grid, it is a reverse effect. When electron hits a grid with highly accelerated electron, when it is missing, it is in the free space. It is only using its kinetic energy to ionize the atoms, thereby ion current measure proportional to pressure. We are measuring pressure. But finally, when it is touching the grid, it produces X-rays. That is how X-rays were discovered. When a high energetic electron hits a target, it produces X-rays. So, it does not matter X-rays, in what way we care for pressure, no, we care. Because these X-rays, they do not have any charge. They put, wherever there is a shadow, it will create, it is like a light. And since collector is a big collector, the X-rays go and touch all this collector because surface area is very high. X-rays will go everywhere. So, X-rays will touch, it produces electrons, photoelectric effect. So, now there will be some electrons coming from this collector and there will be ions which are produced here in the by the accelerated electrons from the atoms available in the residual gas. Those ions also will go to collector, but we are interested in measuring ion when it touches, it takes one electron and gets neutral, and that electron current will be outside measuring as an ion equivalent current. But there is one more electron produced because of X-ray effect. X-rays are producing electron. So, electron out is same as ion in. Ion in also will take one electron from the circuit, electron touching also will go through the circuit. So, this extra electron current coming out of X-rays, that X-rays were produced by accelerated electrons only, but that is now interfering with your ion current and you will get one error called X-ray, that is called X-ray limit at 10 power minus 8 torr. Below that, the electron current coming from the collector due to X-ray falling, which has nothing to do with pressure variations, that dominates much more current compared to the actual current due to reduction of ions and reduction of atoms. That means improvement of vacuum, which we are interested in measuring. That is not happening. Even if pressure is going minus 8, minus 9, minus 10, minus 11, but no variation is coming because of that, because there is a huge background of electrons coming from X-rays. So, this limit has created a problem. So, people thought that we cannot measure below minus 7, minus 8 torr. Like U-tube manometer, we cannot create 1 torr. Suddenly McLeod created a Boyle's law and attached it to U-tube principle and made a McLeod gauge. Same discovery again, two people called Bayard Alpert. What they did was, yes, you are getting X-ray problem. Why? Because it is a big area, cross-sectional area of this collector and X-rays are coming. So, as usual, what they did was simple gimmick. What they did, this filament is brought outside, this filament is brought outside and this collector is brought inside. Instead of cup type of electrode, they have put a thin wire type of electrode and grid is same more or less, but this cup electrode has become thin wire here. This is now an amplified version of this grid. And inside originally filament was there in the ionization gauge, that was brought out, it is outside. I am not showing this bulb for the clarity. Now, as usual, filament produces electrons and they will be accelerated towards ion, that anode grid, sorry not ion, anode grid, and in the process they get confused because of perforated structure and finally they get touch, they produce X-rays, but before that they will ionize, those ions will hit the thin electrode. Point is, ions know whether it is a thin or thick, electric field will drive them anyway and there are not many ions anyway in the high vacuum. So, not big current, thin electrode collector is enough, ion collector. So, this ion will, this electrode will can easily collect, but X-rays will find a problem now, because the very thin wire, amount of area available for X-rays to fall is less now. So, produced electrons out of photoelectric emission due to X-rays is reduced now. So, background error is reduced now. So, X-rays which are not ionized particles, they are photons, they are unable to create error because thin wire is not giving enough cross sectional area for X-rays to fall. But ions, minus 9 also there will be ions, minus 10 also ions, they are finding how these ions are produced, this hot cathode electrons getting accelerated. So, accelerated electron story continues, ionization story continues, which is proportional to pressure, same as the ionization gauge, but X-ray story is less now. So, the X-ray limit is shifted to 10 power minus 11 torr. At 10 power minus 11 minus 12, which is not that important for theoretical scientists, that is okay, but plasma etc., deep space etc., but otherwise minus 11 torr is a very good vacuum. Below that we are not that much interested. At minus 11 torr, even this much thin area for X-rays will dominate. So, X-ray limit is shifted to 10 power minus 11 torr. So, this is a beautiful example of simple manipulation of interchanging the electrodes. It is not even electrode, filament out and collector in, but grid is same. So, ionization principle, ions production proportional to number density and that is proportional to pressure is maintained. And why we are doing ionization? Because at low currents, low pressures, you cannot use thermal principles. Okay. Heat residual gas conduction is buried in the background solid conduction, heat transfer and radiation heat transfer. We cannot use such principles here. Mechanical things P2 minus P1, P1 is 0.1 or 0.01, when P2 is 1000, then that also cannot be used. Only ionization can be used, which is strictly linear function of the pressure. So, lesser the pressure, lesser the ions produced, lesser the atoms with suitable correction factors, and that is how we measure pressure. The X-ray limit is beautifully correlated, solved. This problem is solved by making the inversion of this inner filament outside and outer filament inside. So, this is called Bayard Alpert gauge, which is being routinely used nowadays in the lab for accurate measurements of 11 torr. But all these are hot cathode ionization gauges. If filament gets cut, entire thing has to be thrown. So, there are other cold cathode ionization gauges, which also are calibrated by the spinning rotor gauge we are covering. Their principles, inverted magnetron is another cold cathode. Thus, those things we will cover in the next class, and at the end of that next class, we will also cover little bit about calibration of gauges in general. Thank you very much.